There's a quiet kind of awe that comes with realizing how small we truly are. When you look up at the night sky, those twinkling dots aren't just stars. Many of them are entire galaxies, each holding billions of suns, planets, and maybe even life. Every point of light is a distant cosmic city, shining from unimaginable distances across the universe. And if you want to uncover the mind-bending truth behind them, watch this video till the end and subscribe to the channel. Let's begin. When we look out into that endless ocean of galaxies, it's easy to feel as though the universe stretches on forever. But even our view of infinity has limits. This visible portion of reality is what astronomers call the observable universe. It's everything we can possibly see, bounded not by walls, but by time itself. Because light travels at a finite speed, about 300,000 kilometers per second, we can only see as far as light has had time to reach us since the dawn of creation, roughly 13.8 billion years ago. Yet, due to the expansion of space, those farthest objects we can detect are now about 93 billion light-years apart. Beyond that lies the unobservable, regions forever hidden, where light hasn't yet arrived. So, when we gaze deep into space, we're not seeing the universe as it is now, but as it once was, stretched across time and distance in a shimmering sphere of visibility. It's like standing at the edge of a cosmic window, aware that beyond what we can see lies an immeasurable vastness, silent and unknowable. And within that visible bubble lies something even more astonishing. Not just billions, but trillions of galaxies, each one a universe unto itself, waiting to be counted. Counting galaxies may sound like an impossible task, and in truth, it almost is. For centuries, astronomers believed our Milky Way was the entire universe. But as our telescopes grew sharper, our ignorance unraveled. The real breakthrough came with the Hubble Space Telescope, which in the 1990s performed one of the most remarkable experiments in human history, the Hubble Deep Field. Astronomers pointed the telescope at what seemed to be an empty patch of sky, a tiny area no larger than a grain of sand held at arm's length, and let it stare for days. What returned was breathtaking. Not darkness, but thousands of galaxies, each one filled with billions of stars. That single speck of sky revealed that the universe was far more crowded than anyone had dared imagine. Using such data, scientists began estimating that there are at least 2 trillion galaxies in the observable universe. And then came the James Webb Space Telescope, the most advanced eye humanity has ever opened to the cosmos. Webb sees deeper into time, detecting galaxies so ancient and faint that their light has been stretched by the expansion of the universe itself. What it revealed shattered expectations. Even in the earliest eras of the cosmos, just a few 100 million years after the Big Bang, galaxies already thrived in numbers and sizes we didn't think possible. Each new observation shows us that our early accounts were only a fraction of the truth. The universe is not a static collection of galaxies. It's a living sea of creation, teeming with more cosmic islands than we can ever hope to chart. And within that incomprehensible multitude lies our home, one humble spiral among trillions. If the universe is a vast cosmic ocean, then each galaxy is an island, a glowing city of stars adrift in endless darkness. To truly grasp the immensity of the cosmos, we must narrow our gaze to just one of these islands, our own Milky Way galaxy. From our small perch within it, we see the night sky as a dome of scattered lights, unaware that we're actually inside a colossal, rotating disk of stars, gas, dust, and dark matter, stretching over 100,000 light-years across. The Milky Way is home to somewhere between 100 and 400 billion stars, and orbiting many of those stars are planets, billions upon billions of worlds, each with its own conditions, its own stories, its own mysteries. Our solar system sits in a quiet suburban region of this immense structure, tucked away in one of its spiral arms known as the Orion Arm, about 27,000 light-years from the galactic center. From this vantage point, we orbit the Milky Way's core once every 230 million years, a single galactic year. That means the last time Earth was in this same position in the galaxy's orbit, dinosaurs had only just begun to roam our planet. Our entire species, civilization, and recorded history are just fleeting sparks in the grand timeline of this single galaxy's existence. The heart of the Milky Way is not a peaceful place. At its very center lies a supermassive black hole called Sagittarius A, a gravitational titan with the mass of over 4 million suns. It serves as the anchor for our entire galaxy, holding it together through its immense gravitational influence. Around it, stars whirl at incredible speeds, and clouds of gas and dust spiral inward like water down a cosmic drain. Occasionally, it flares with bursts of radiation as it consumes matter from its surroundings, a quiet reminder of the powerful forces that shape the universe. But the Milky Way is not just a collection of stars. It's a living, evolving entity. New stars are born within enormous molecular clouds, cold, dark regions filled with gas and dust that collapse under their own gravity. In the glowing arms of our galaxy, stellar nurseries shine brightly in nebulae such as the Orion Nebula and the Eagle Nebula, where young stars are ignited and planetary systems begin to form. Elsewhere, ancient stars burn dimly in globular clusters, orbiting like distant memories of the galaxy's youth. Some stars die spectacularly in supernova explosions that scatter heavy elements into space, the same elements that eventually form planets and even life itself. Every atom of iron in our blood and every atom of calcium in our bones was forged inside one of these long-dead stars. The Milky Way is, in every sense, a self-sustaining cosmic ecosystem. Stars are born, live, die, and their remains become the building blocks for new generations. Even our own sun is a product of this cycle. It was born roughly 4.6 billion years ago from the ashes of earlier stars, and it will burn for another 5 billion years before expanding into a red giant and eventually shrinking into a white dwarf. By that time, humanity, if it still exists, may have spread far beyond this single star system, perhaps even beyond this galaxy itself. When astronomers map the Milky Way, they see not a flat, rigid disk, but a slightly warped spiral, with curving arms rich in new star formation and a bright central bulge filled with older stars. Beyond the visible disk lies a vast, invisible halo of dark matter, an unseen structure that makes up most of the galaxy's mass. This dark matter provides the gravitational glue that keeps our galaxy intact, ensuring that its outer stars don't simply drift away into the void. Without it, the Milky Way would tear itself apart. Despite its grandeur, the Milky Way is not particularly special among galaxies. It's roughly average in size and structure, a barred spiral, like countless others scattered across the cosmos. Yet for us, it holds profound meaning. Every story ever told, every thought ever dreamed, every life that ever was or will be, all of it has taken place within this single galactic island. Our history is written not just on Earth, but on the Milky Way itself. It's our cosmic cradle, a home that has nurtured us without our even realizing it. Now consider this. If our galaxy alone contains hundreds of billions of stars, and if each of those stars might host planets, then even a conservative estimate suggests there could be tens of billions of potentially habitable worlds in the Milky Way. Multiply that by the 2 trillion galaxies believed to exist, and you begin to see the unfathomable magnitude of the universe. there could be sextillions of planets, a number so large that it defies human language. Somewhere out there, among those countless worlds, life could be thriving under alien suns, unaware of us, just as we are unaware of them. And yet, for all its vastness, the Milky Way is only one thread in the immense cosmic tapestry. It belongs to something far larger, a colossal network of galaxies stretching across the universe, connected like neurons in a vast cosmic brain. This is known as the cosmic web, and it's where our journey takes us next. From the single spiral of the Milky Way to the grand architecture of the universe itself, where galaxies gather, cluster, and flow in patterns too immense for the human mind to fully grasp. When we pull back from the Milky Way, far beyond its spiral arms, its clusters, its halo of dark matter, we begin to see a pattern that redefines the very shape of existence. The universe, at its grandest scale, is not random chaos. It is structured, intricate, and breathtakingly organized. Astronomers call this grand arrangement the cosmic web, a vast, three-dimensional lattice of galaxies, filaments, and voids stretching across the cosmos like the neural network of some unfathomable mind. Imagine zooming out from our galaxy until the Milky Way itself becomes just a glowing dot. Then zoom out further until that dot joins countless others, each representing a galaxy. You'd see that galaxies are not evenly scattered through space. They are drawn together by gravity into massive clusters and superclusters, which connect to one another through long, luminous filaments made of dark matter, gas, and light. Between these filaments lie immense voids, vast regions almost completely empty, spanning hundreds of millions of light years. In these voids, there are no galaxies, no stars, just the quiet hum of intergalactic darkness. This web-like structure was first hinted at in the late 20th century when astronomers began mapping the positions of galaxies using powerful telescopes. What they found was astonishing. The universe resembled a colossal sponge, or more poetically, a cosmic spiderweb, with galaxies woven into filaments that crisscross the void. The largest of these structures discovered so far, such as the Hercules Corona Borealis Great Wall, stretches over 10 billion light-years, so immense that light, traveling at its incredible speed, would take 10 billion years to move from one end to the other. To put that into perspective, that's almost as old as the universe itself. The filaments of the cosmic web are like rivers of galaxies, flowing along invisible currents of dark matter, the mysterious substance that makes up roughly 27% of the universe. Though we cannot see dark matter directly, we can trace its presence through its gravitational effects. It pulls galaxies together, shapes their movement, and forms the scaffolding on which the visible universe is built. Think of dark matter as the unseen framework, the bones of the cosmos, while galaxies and stars are the luminous flesh draped upon it. At the intersections of these filaments, gravity's pull becomes strongest, and that's where we find the most massive galaxy clusters, titanic cities of hundreds or thousands of galaxies bound together. These clusters themselves form superclusters, sprawling cosmic metropolises connected across unimaginable distances. The Milky Way belongs to one such supercluster known as Laniakea, meaning immeasurable heaven in Hawaiian. This vast region, stretching over 500 million light-years, contains over 100,000 galaxies, all moving together through space like a drifting continent in a cosmic sea. But what's truly mind-bending is the scale of emptiness between these filaments. The voids are enormous cosmic deserts, where matter is almost absent. Some of these voids span more than 500 million light-years across, containing only a handful of lonely galaxies, or none at all. These silent gaps are reminders that even the universe's grandest structures are defined as much by emptiness as by matter. The cosmos is not full, but mostly hollow. a magnificent pattern of something and nothing intertwined. Simulations of the early universe show that this web began forming just a few 100 million years after the Big Bang. Tiny quantum fluctuations in the density of matter gradually grew under gravity's relentless influence. Over billions of years, matter flowed along these gravitational wells, pooling into galaxies and clusters while leaving the voids to expand. In essence, the universe sculpted itself into a web of light and shadow, a masterpiece painted by gravity across the canvas of space-time. What's even more astonishing is how eerily similar this structure is to the neural networks within a human brain. Both are systems of nodes connected by filaments, both governed by complex interactions that give rise to emergent patterns. Some scientists have even noted that if you compared a map of the cosmic web with a microscopic image of neurons, the two would look strikingly alike. It's as though the universe itself is thinking, an infinite mind reflecting its structure in everything it creates, from the smallest cells to the largest clusters of galaxies. And as we map more of this cosmic web using deep space surveys and gravitational lensing, we continue to find larger and more complex arrangements. Some filaments span hundreds of millions of light years, curving through space like rivers of galaxies. Others twist and braid, forming knots where the brightest and most massive galaxies ignite. The deeper we look, the more we see that the universe is not random chaos. It's a vast, interconnected system, a kind of cosmic architecture built on laws of gravity, motion, and time. When you stand beneath the night sky, you are not merely looking at stars scattered randomly across blackness. You are peering through the threads of this immense web. Our Milky Way sits on one filament of that structure, like a pearl on a cosmic string, linked to other galaxies through invisible threads of gravity. The light from distant clusters travels along these same filaments, weaving the story of the cosmos into our telescopes, our instruments, and our imaginations. The cosmic web reminds us that the universe is not only vast, it is alive with structure, order, and beauty. It is a grand symphony of matter and motion, a testament to the elegance of natural law. And through this intricate web, light itself journeys endlessly, carrying with it the memories of creation, ancient photons that left their galaxies billions of years ago, now whispering to us across the gulf of time. That light, those ancient messages from the edge of eternity, are our next key to understanding the universe. For in every beam of starlight lies a secret, that looking into space is not merely looking outward, but looking backward in time. When you gaze into the night sky, you are not seeing the universe as it is, you're seeing it as it was. Every shimmer of starlight, every faint glow of a distant galaxy is a message sent long ago, traveling across the vast ocean of space to reach your eyes. In this way, light is a time machine, carrying with it the stories of the cosmos across billions of years. The deeper we look into space, the further back in time we are peering, not metaphorically, but literally. Light, though unimaginably fast, is not instantaneous. It moves at a finite speed, about 300,000 kilometers per second, the fastest velocity possible in nature. That means even the light from our own sun, which seems to shine in real time, takes 8 minutes to reach Earth. If the sun were to suddenly vanish, we wouldn't know it until 8 minutes later. The light from the nearest star system, Alpha Centauri, takes more than 4 years to get here. From the Andromeda Galaxy, our nearest major galactic neighbor, light needs about 2.5 million years to arrive. So when you look at Andromeda through a telescope, you are witnessing it as it was when early humans were first learning to use stone tools. Now, stretch that concept to the scale of the entire cosmos. When astronomers aim powerful telescopes like Hubble or James Webb into deep space, they aren't just photographing distant galaxies. they're uncovering the ancient history of the universe. The light from galaxies billions of light years away began its journey when the cosmos itself was young. Some of the faintest, reddest galaxies detected by the James Webb Space Telescope are so far away that their light has been traveling for over 13 billion years. In other words, Webb is showing us galaxies that existed when the universe was less than 300 million years old, a time when the first stars were still igniting from the cosmic darkness that followed the Big Bang. It's a concept so profound, it almost defies comprehension. The deeper we peer into space, the further back we travel in time. Every observation is an excavation of the universe's past, layer by layer, photon by photon. In a very real sense, telescopes are time portals, not just instruments of sight. They allow us to watch the unfolding of cosmic history, the birth of stars, the collisions of galaxies, the flicker of quasars that burned when Earth itself did not yet exist. When you see a distant galaxy glowing faintly on a telescope image, you are witnessing a cosmic fossil, light that has journeyed unbroken for billions of years through expanding space, through intergalactic dust, through the gravitational fields of unseen dark matter. Some of those photons may have left their galaxies before our sun, before our planet, before life itself. They've crossed a universe that has grown and stretched since they began their voyage. By the time they arrive, the galaxies they came from may have already changed completely. Stars born and died, planets formed and vanished, black holes awakened and consumed entire regions of space. We are not seeing those galaxies as they are. We are seeing their ghosts, preserved in the light that still travels toward us. This phenomenon is what makes astronomy unlike any other science. Astronomers cannot experiment directly with galaxies or stars. They cannot touch, move, or alter them. Instead, they read the universe's autobiography, written in light. Each photon carries information about the chemical composition of stars, the motion of galaxies, even the presence of planets orbiting distant suns. When that light is analyzed through instruments called spectrometers, it reveals secrets that no human eye could ever see. The fingerprints of elements, the motion of entire galaxies, the history of creation itself. In a sense, the night sky is a living archive of the past. When we look at the moon, we see it as it was 1.3 seconds ago. When we look at the sun, we see it 8 minutes in the past. The light from the Pleiades star cluster is 400 years old, meaning that some of the photons that touch your eyes tonight left their stars around the time Galileo first turned a telescope toward the heavens. The light from the farthest known galaxies, those barely visible smudges in the deep field images, is over 13 billion years old, carrying us back to a time when the first galaxies were flickering to life in the young universe. Even the cosmic microwave background radiation, the faint afterglow that fills all of space, is the oldest light of all, a remnant from 380,000 years after the Big Bang, when the universe was still an infant. It's the ultimate time capsule, a map of the universe's first moments. Every direction we look, that ancient light surrounds us, whispering of a time before stars, before galaxies, before even atoms as we know them. And here's the beautiful irony. As much as we use light to see the past, we are also watching the universe change through that very lens. Some of the galaxies whose ancient light we see today might no longer exist in their original form. They may have collided, merged, or been torn apart by gravitational tides. The light we see is a memory, a snapshot frozen in time, while the reality, countless billions of light years away, has already moved on. It's as though the cosmos itself is a vast museum of light, and every beam we capture is a relic of a bygone era. To look into space is to see history unfolding not in words or stone, but in photons, the oldest travelers in existence. We are both the observers and the beneficiaries of their journey, privileged to catch their faint glimmer before it fades forever into the expanding dark. And as we trace this light, this flowing river of time, we begin to understand something even deeper, that the galaxies sending us their glow are not static relics. They are alive, dynamic, and ever-changing. Just as the universe evolves, so do the galaxies themselves, growing, colliding, dying, and being reborn. When we think of galaxies, we often picture them as serene spirals suspended in the quiet of space, frozen, unchanging, eternal. But the truth is far more astonishing. Galaxies are alive, not alive in the way a creature is, but alive in motion, transformation, and evolution. They are cosmic ecosystems, constantly changing, feeding, growing, colliding, and dying. Each one is a dynamic organism made not of flesh and bone, but of stars, gas, dust, and dark matter. And they evolve over billions of years in a breathtaking dance of creation and destruction. The life of a galaxy begins in the deep past, born from the cosmic debris left behind after the Big Bang. In the beginning, the universe was a near-uniform sea of hydrogen and helium gas, gently rippled by tiny fluctuations in density. Over time, gravity amplified these fluctuations, pulling matter together into the first proto-galactic clouds. Within these collapsing regions, the first stars ignited, blazing with blue-white fury and flooding space with light for the first time. These early stars lived fast and died violently, their supernovae enriching the surrounding gas with heavier elements, the raw materials for future stars, planets, and eventually life. From these primordial structures emerged the first galaxies, roughly 500 million years after the Big Bang. They were small and irregular, like cosmic seedlings. Over billions of years, these baby galaxies began to merge, drawn together by gravity into ever larger systems. This process, the hierarchical assembly of galaxies, is how the grand spirals and massive ellipticals we see today were born. Every large galaxy, including our Milky Way, carries within it the remains of countless smaller galaxies it has absorbed throughout its long life. The stars of those devoured systems now orbit quietly in our galactic halo, like ancient memories of cosmic cannibalism. These mergers are among the most dramatic events in the universe. When two galaxies collide, they don't crash like solid objects. The space between their stars is so vast that very few stars actually hit one another. Instead, their gravitational fields tear and twist them apart, warping their shapes into stunning new forms, tidal tails, ring structures, and starburst regions where new stars ignite in furious numbers. A galactic collision is both violent and beautiful, an act of destruction that simultaneously sparks creation. Gas clouds compress under immense gravitational pressure, birthing waves of new stars, while others are flung into intergalactic space. Our own Milky Way is not immune to this process. In fact, it has been shaped by it. Over its lifetime, the Milky Way has absorbed dozens of smaller galaxies, their remnants now detectable as faint streams of stars stretching across the sky. And in about 4 billion years, we are destined for a spectacular collision of our own, a slow, spiraling dance with the nearby Andromeda galaxy. The two will merge into a new, larger elliptical galaxy, sometimes nicknamed Milkomeda. During the merger, the night sky will be filled with blazing arcs of stars, and the shapes of both galaxies will distort into breathtaking tendrils of light. It will be the end of the Milky Way as we know it, and the birth of something even grander. But not all galaxies are spirals or collisions in progress. Some have grown so old and massive that they've burned through most of their gas, the fuel for new stars. These elliptical galaxies, enormous and glowing red, are like ancient giants nearing the end of their lives. They no longer create new stars. Instead, they quietly fade as their remaining stars age and die. Eventually, many of those stars will become white dwarfs, neutron stars, or black holes, leaving behind a diffuse glow, the dying embers of once luminous cosmic cities. In contrast, spiral galaxies like our own are still vibrant with life. Their swirling arms are stellar nurseries, rich with gas and dust that fuel constant cycles of birth and death. Within these arms, dense clouds collapse into new stars, and when those stars die, their explosions recycle the material back into the galaxy, seeding the next generation. It's a continuous process, a galactic heartbeat that keeps the cosmos alive. Even irregular galaxies, those distorted and misshapen forms scattered throughout the universe, have their own kind of beauty. Many of them are galaxies caught mid-collision or torn apart by gravitational tides from nearby giants. Some are newly forming, others are the stripped-down remnants of once great systems. In all cases, their shapes tell stories of encounters, violence, rebirth, and time. Galaxies are also influenced by mysterious cosmic forces that extend beyond visible matter. The presence of dark matter, which outweighs normal matter 5-to-1, acts as a stabilizing halo, holding galaxies together and preventing them from flying apart as they rotate. Without it, the graceful spirals we see would simply dissolve into chaos. Over billions of years, dark matter has guided the growth and structure of galaxies like an invisible architect, shaping the skeleton of the cosmic web itself. And at the heart of nearly every large galaxy lies a supermassive black hole, a gravitational engine millions or billions of times the mass of our Sun. These titans play a crucial role in galactic evolution. When they feed, they unleash staggering amounts of energy, driving powerful winds and jets that can either trigger or shut down star formation. In their quiet phases, they anchor the galaxy's core, exerting influence over the motion of surrounding stars. It is one of the most poetic paradoxes of the cosmos, that the most destructive force in the universe is also one of its greatest architects. The story of galaxies, then, is a story of transformation, birth from chaos, growth through merger, maturity through balance, death through exhaustion. Yet even galactic death is not truly an end. The stars they created live on, wandering the intergalactic dark or finding new homes in larger systems. In this sense, the universe itself recycles endlessly, its materials reshaped and reborn over cosmic timescales. So when we look at a distant galaxy through a telescope, we are not seeing a static object. We are witnessing a living process, frozen in one moment of its evolution. It may be a newborn galaxy, blazing with the fires of creation, or a middle-aged spiral, rich with stars and worlds, or a dying elliptical, fading into twilight. Each one is a snapshot in an endless cycle that has been playing out for billions of years and will continue long after our world is gone. And as we uncover these truths, another mystery deepens, because everything we see, from the blazing cores of galaxies to the faintest intergalactic glow, makes up less than 5% of the total universe. The rest, an invisible realm of dark matter and dark energy, is what truly governs the cosmos. When we look out into the vastness of space, at the galaxies, the stars, the glowing nebulae, it's tempting to believe we're seeing the full grandeur of the universe. But the shocking truth is that everything we can see, every planet, star, and galaxy, makes up less than 5% of what actually exists. The rest, a staggering 95%, lies hidden in the shadows of reality, invisible and mysterious. Scientists call this unseen majority the dark universe, and it consists of two great cosmic enigmas: dark matter, and dark energy. The story of the dark universe begins with a problem, one that astronomers first noticed in the early 20th century. When they studied how galaxies spin, they found something that didn't make sense. The outer stars in galaxies, like those in our Milky Way, were moving far faster than the laws of gravity should allow, based on the visible mass of stars and gas. According to Newton and Einstein, these galaxies should have flown apart, yet they held together. The only explanation was that something unseen was providing the extra gravity necessary to bind them. This invisible glue became known as dark matter. It doesn't emit or absorb light, doesn't reflect, and can't be seen directly, but its gravitational fingerprint is unmistakable. It forms vast halos around galaxies, extending far beyond the visible disk, holding everything together. Without dark matter, the Milky Way would simply dissolve. Its stars would drift apart into the void. It's not just present in galaxies either. Dark matter weaves through the entire cosmic web, acting as the scaffolding upon which galaxies and clusters are built. We know it exists because of how it bends and distorts light, a phenomenon called gravitational lensing. When light from distant galaxies passes through regions rich in dark matter, its path curves, creating warped or magnified images. By studying these distortions, scientists can map where dark matter is, even if they can't see it directly. What they've discovered is astonishing. For every gram of visible matter in the universe, there are roughly 5 grams of dark matter. Yet we still have no idea what it's made of. It might consist of exotic particles that barely interact with ordinary atoms, so elusive that they pass right through Earth and through us without leaving a trace. But if dark matter explains the structure of the universe, dark energy explains its behavior, and its mystery runs even deeper. In the late 1990s, astronomers studying distant supernovae made a discovery that upended our understanding of cosmology. They expected to find that the universe's expansion, driven by the momentum of the Big Bang, was gradually slowing down under gravity's pull. Instead, they found the opposite. The universe's expansion is accelerating. Space itself is stretching faster and faster over time. The cause of this acceleration was named dark energy, a force so powerful and so strange that it makes up about 68% of the total universe. Unlike gravity, which pulls matter together, dark energy pushes space apart. It's not energy in the conventional sense. We don't know what form it takes or where it resides. Some theories suggest it's an inherent property of space itself, the cosmological constant Einstein once proposed and later dismissed as his greatest blunder. Others think it might be a new kind of field or particle that permeates all of existence. Whatever it is the dominant force of the cosmos, dictating its ultimate fate. The implications are staggering. Because of dark energy, galaxies that are already far away are receding from us at ever-increasing speeds. Eventually, many of them will move faster than light relative to us. Not because they are moving through space that fast, but because space itself is expanding between us and them. When that happens, their light will never reach us again. They will fade beyond our cosmic horizon, vanishing forever from human view. This means that every moment we look at the night sky, we are seeing a smaller and smaller portion of the total universe. The cosmic web we mapped and studied, that grand lattice of galaxies, is slowly unraveling from our perspective. Hundreds of billions of galaxies will eventually disappear from detectability, leaving only our local group, a few dozen galaxies bound together by gravity, as our visible island in an ever-darkening sea. The future universe will grow emptier, colder, and quieter as dark energy continues its relentless expansion. What's haunting about this is that we are living at a very special time, a fleeting moment when we can still see the universe in all its richness, before most of it slips beyond sight forever. Millions of years from now, cosmic observers, if any exist, might look into their skies and see only their own galaxy, unaware that the universe was ever filled with countless others. The grand cosmic truth we've discovered, that we are part of a vast and expanding universe, could one day vanish from observable reality, erased by the very energy that sustains it. Dark matter and dark energy together shape everything we know and everything we don't. One sculpts the form of the cosmos, while the other dictates its destiny. And yet, despite their dominance, we remain profoundly ignorant about them. What are these invisible components made of? Why do they exist in the proportions they do? And what do they reveal about the deeper nature of reality? These questions lie at the cutting edge of modern physics, where science begins to blur into philosophy. So, in the grand cosmic equation, everything that we can see, the stars, the galaxies, the light itself, is just the tip of an unfathomable iceberg. Beneath it lies an unseen universe, vast and powerful, whispering secrets we've only begun to hear. The visible cosmos may be the face of creation, but the dark universe is its beating heart, the hidden force shaping the fate of everything. And as we confront these invisible mysteries, our sense of scale must once again expand, because even within the observable universe, the numbers themselves defy comprehension. The next step in our journey brings us face to face with the sheer immensity of existence, a reality so vast that language fails to capture it, the scale of trillions. The numbers that describe our universe are so vast that they almost lose meaning. They slip through the fingers of comprehension like water through sand. Yet to truly grasp the scale of trillions, we must try to wrap our minds, however imperfectly, around the enormity of it all. For everything we've seen, every dazzling nebula, every spiral galaxy, every cluster of light in the cosmic web, is only a fraction of what exists. The observable universe alone is home to around 2 trillion galaxies, each one holding hundreds of billions of stars, and many of those stars with their own families of planets. Let's pause and try to visualize that. Imagine standing on a beach, holding a single grain of sand between your fingers. That grain represents one galaxy, an immense island of light containing perhaps 300 billion stars, countless planets, and maybe even civilizations. Now imagine the entire beach, every grain of sand on it, each one representing another galaxy. The number of grains of sand on all the beaches on Earth combined is estimated to be around 7.5 quintillion, a number so large it defies intuition. Yet even that might not be enough to represent every galaxy in the observable universe. If every galaxy were one grain of sand, the universe would not be a single beach. It would be an infinite coastline, stretching beyond the horizon in every direction, disappearing into eternity. Within just our own Milky Way, there are roughly 100 to 400 billion stars, and if even a small percentage of those stars have planets, then we're talking about tens of billions of potentially habitable worlds in just one galaxy. Multiply that by 2 trillion galaxies, and you get a number so large that it begins to transcend mathematics. Roughly 10 to the 24th power planets. That's a 1 followed by 24 zeros. There may be more worlds in the universe than there are grains of sand on Earth. Each one is a possible cradle of life, each one orbiting a sun of its own, some long dead, others yet to form. Think about this staggering truth. If you were to travel across the observable universe at the speed of light, the ultimate cosmic speed limit, it would take you 93 billion years to go from one side to the other. But even that immense distance represents only what we can currently see. Beyond that lies the unobservable universe, potentially infinite in size, filled with even more galaxies, that will forever remain beyond our reach. To bring it closer to human perspective, let's shrink the scale. If the Milky Way were reduced to the size of a single coin, the Andromeda Galaxy, our nearest large neighbor, would be another coin about 2 feet away. The entire observable universe on that same scale would be larger than Earth itself, filled with coins scattered through space, each one a galaxy, each one containing billions of stars. We live in a universe so immense that even metaphors begin to break beneath its weight. Yet the most mind-bending part of this reality is not just its size, but its density of meaning. Every galaxy is a potential universe unto itself, with its own history, its own evolution, and its own story written in light. Some of those galaxies are long dead, their stars cooled and extinguished. Others are newborn, fiery and chaotic, still sculpting their first planets. Each one is a single sentence in the grand story of creation, and together they form an epic beyond imagination. When we talk about trillions of galaxies, we are really talking about trillions of chances for life, for creation, for beauty, for mystery. Somewhere on one of those countless worlds orbiting a distant star, perhaps another being is looking up at their sky, wondering if they are alone. They may never know that we exist, just as we may never know of them, yet both of us are part of the same cosmic tapestry, woven from the same ancient atoms forged in long-dead stars. This realization reshapes everything we think we know about existence. It humbles the ego, softens the boundaries of the self, and replaces isolation with connection. When you grasp the scale of trillions, you begin to see that we are not small because the universe is vast. We are vast because we are part of it. Every atom in your body was born in a star billions of years ago, in a galaxy that may have long since disappeared. You are a piece of the universe, reflecting on itself. And yet, for all its immensity, the cosmos has a kind of intimacy, because we belong to one tiny corner of it, one small galactic neighborhood we call home. Our next step takes us there, to our own little corner of the cosmic web, where the Milky Way lives among its neighbors in a quiet cluster of galaxies moving together through the endless dark. If the universe is an infinite city of light, then the Milky Way resides in one of its countless neighborhoods, a small yet bustling district called the local group. This is our galactic family, a gravitationally bound collection of more than 80 galaxies, ranging from colossal spirals like our own to tiny, dim dwarf galaxies barely large enough to host a few million stars. Together, these galaxies drift through the silent expanse of intergalactic space, moving in a slow, intricate dance that has been unfolding for billions of years. At the heart of this local group are its two giants, the Milky Way and the Andromeda Galaxy. These two massive spirals dominate the region, each with hundreds of billions of stars and immense halos of dark matter that stretch far beyond their visible disks. They are separated by about 2.5 million light-years, but their mutual gravity ensures that they are not just neighbors, they are destined to meet. Over the next 4 billion years, the Milky Way and Andromeda are on a collision course, slowly drifting toward one another at a speed of roughly 110 kilometers per second. This cosmic encounter will be one of the most spectacular events in the history of our local group. When they finally collide, their graceful spiral arms will warp and twist under gravity's pull, flinging stars into vast tidal tails that stretch across intergalactic space. The two galaxies will merge, not in an explosive crash, but in a slow gravitational waltz, taking billions of years to fully combine. When the dance is over, they will form a new, larger elliptical galaxy, a single, brilliant structure glowing with the combined light of more than 1 trillion stars. For now, though, they are still distinct, two luminous spirals watching each other from across the cosmic gulf, locked in an ancient embrace that will one day reshape our sky. Orbiting these two giants are a host of smaller galaxies, faint companions that populate the local group like cosmic satellites. The Milky Way alone has over 50 known dwarf galaxies in its orbit. Some of the most prominent are the Large and Small Magellanic Clouds, visible from the southern hemisphere as two misty patches of light. These galaxies are irregular in shape, and both are being gradually torn apart by the Milky Way's gravity, their stars and gas stripped away to form long, glowing trails across the night sky. They are, in a sense, our galaxy's cosmic companions, helping to feed its growth even as they are consumed by it. Andromeda, too, has its own entourage of dwarfs, like the Triangulum galaxy, M33, the third largest member of the local group. Triangulum is a smaller spiral galaxy, about 60,000 light-years across, and though it's dwarfed by its neighbors, it is no less beautiful. Some astronomers believe that Triangulum may one day play a role in the Milky Way-Andromeda merger, perhaps being drawn in as part of their gravitational collision. Surrounding these major players are dozens of tiny galaxies, faint, irregular, and diffuse, the cosmic leftovers of earlier ages. Some, like Leo Y or Sagittarius Dwarf, are so faint that they were discovered only in recent decades, hiding at the edge of detectability. If we could zoom out and view the local group as a whole, we'd see a region about 10 million light-years across, shaped somewhat like an elongated bubble. At its center sit the Milky Way and Andromeda, their surrounding satellites orbiting like moths around twin flames. Farther out, we find isolated dwarfs such as the IC 1613 and Wolf-Lundmark-Melotte WLM galaxies, drifting near the outskirts. The entire local group itself is not floating aimlessly. It's moving as part of something even grander, being drawn by the immense gravitational pull of nearby galaxy clusters and superclusters. In particular, our local group is part of a much larger structure called the Laniakea supercluster, a vast region of space spanning over 500 million light-years, containing more than 100,000 galaxies. The name Laniakea, meaning immeasurable heaven in Hawaiian, is profoundly fitting. It reminds us that even our immense local group, containing hundreds of billions of stars, is just a speck within this immeasurable cosmic web. Within Laniakea, our local group is moving toward a dense region known as the Virgo cluster, which acts as one of the gravitational anchors of our supercluster. Beyond Virgo lies the Great Attractor, an even more mysterious gravitational anomaly pulling thousands of galaxies toward it, including our own. When astronomers map the motion of the galaxies in our region of the universe, they can see these gravitational influences clearly. The Milky Way and Andromeda are not just moving toward each other. Together, the entire local group is hurtling through space at nearly 600 kilometers per second, drawn by the invisible pull of mass concentrations, billions of light-years away. We are not stationary. We are travelers, carried along on an invisible cosmic current through the vast, ever-shifting sea of the universe. Despite its grandeur, the local group has a kind of intimacy. Within it, galaxies are close enough, on cosmological scales, to interact, to influence one another, to trade gas and stars through gravitational tides. It's a family of sorts, one bound not by proximity in the human sense, but by the invisible fabric of gravity. Every galaxy here has its role in the greater ecosystem. The large spirals shaping the gravitational balance, the dwarfs feeding and enriching them with new material, and the intergalactic medium, the thin gas between galaxies, serving as the connective tissue through which the group evolves. For now, the Milky Way sits in a relatively quiet corner of this neighborhood. Our galaxy's nearest known neighbor, the Canis Major dwarf galaxy, lies a mere 25,000 light-years from the Sun, almost hidden behind the dense curtain of the Milky Way's disk. Yet even this small companion is slowly being absorbed, its stars stretching into faint streams that wrap around our galaxy like ribbons of ancient starlight. In every direction, the gravitational interplay continues. Galaxies collide, merge, and consume one another, while others drift in solitude at the fringes, too far to join the fray. If you were to stand outside the Milky Way, far enough to see the local group as a whole, you would witness a breathtaking sight. Two massive spirals glowing with billions of stars, surrounded by swarms of faint companions, all suspended in the velvet black of intergalactic space. Between them lies a tenuous bridge of gas and dark matter, a gravitational tether binding the Milky Way and Andromeda together. The entire ensemble drifts slowly toward its destiny, to merge and reshape into a single, larger galaxy. One small transformation in an endless cosmic cycle. And that's the truth about our place in the grand cosmic web. We are not isolated, but connected, part of a galactic family, moving together through an expanding universe. Every star you see in the night sky belongs to this local domain, this humble corner of the cosmos that we call home. Yet even as our local group binds together through gravity, the larger universe around it continues to expand, stretching the fabric of space itself. The galaxies beyond our gravitational reach are moving away faster and faster, carried by the relentless expansion of the cosmos. The universe is not static. It is alive with motion, swelling, stretching, and evolving with every passing moment. The space between galaxies is expanding, not because they are moving through space, but because space itself is growing. This is one of the most profound and counterintuitive truths in all of science. The cosmos is not simply a vast container of stars and galaxies. It is a dynamic fabric, constantly reshaping and stretching under its own laws. Every point in the universe is moving away from every other point, carried outward by the expansion of space itself, an expansion that began nearly 13.8 billion years ago in the event we call the Big Bang. When Edwin Hubble first looked through his telescope in the 1920s and measured the light from distant galaxies, he noticed something extraordinary. The light was redshifted, stretched to longer, redder wavelengths. This meant the galaxies were receding from us, and not just in random directions. The farther away a galaxy was, the faster it was moving away. This linear relationship between distance and speed became known as Hubble's law, and it was the first solid evidence that the universe is expanding. At first, many imagined galaxies flying apart like fragments from an explosion. But that's not quite right. The Big Bang did not happen at a single point in space. It happened everywhere at once. It was not an explosion in space, it was an explosion of space. The universe didn't expand into anything. Rather, space itself began to stretch, and it's been stretching ever since. Every galaxy, every cluster, every patch of cosmic fabric is caught in this ongoing expansion. To picture this, imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move away from each other, not because they are moving on their own, but because the surface itself is expanding. No matter which dot you stand on, it looks as though all the others are moving away from you. That's exactly what's happening in the universe, from any vantage point. Earth, another galaxy, or even a faraway cluster. It appears that everything else is receding. There is no true center of the expansion, because everywhere is expanding simultaneously. In the early universe, this expansion was rapid and chaotic, but gravity worked to slow it down as matter clumped together into galaxies and clusters. For billions of years, scientists believed that the expansion might one day halt, or even reverse, leading to a big crunch. But in the late 1990s, observations of distant supernovae revealed something completely unexpected. the expansion wasn't slowing down at all. It was accelerating. The culprit behind this cosmic acceleration is the mysterious force we now call dark energy, a phenomenon that acts as a kind of anti-gravity, pushing galaxies apart and driving the universe's growth at an ever-increasing rate. The consequences of this are staggering. Galaxies that are already distant are receding from us faster than those nearby. And as the universe continues to expand, they'll eventually reach speeds that exceed the speed of light. Not because they are moving faster than light through space, but because space itself is expanding faster than light can cross it. When that happens, their light will never reach us again. They will slip beyond our cosmic horizon, vanishing forever from observable reality. In time, the night sky will grow emptier. The grand cosmic web will fade as distant galaxies drift away, leaving only our local group, the Milky Way, Andromeda, and their companions, gravitationally bound together, an island of light in an endless dark sea. The rate of this expansion is measured by the Hubble constant, a number that tells us how fast galaxies move apart per unit of distance. But even this constant is full of mystery. Modern measurements using different methods, from the cosmic microwave background to observations of supernovae and variable stars, produce slightly different results, suggesting that our understanding of the universe's growth may still be incomplete. Some scientists speculate that this tension hints at new physics. Perhaps dark energy itself is evolving, or maybe there are hidden dimensions or unknown forces at work. To understand just how deeply expansion defines our universe, consider this. Every second, the cosmos grows by billions of kilometers. Galaxies separated by vast voids of space are being carried farther apart as the very fabric of space-time stretches. On smaller scales, however, gravity still reigns supreme. It binds stars into galaxies, galaxies into clusters, and clusters into superclusters. The expansion doesn't tear apart solar systems or even galaxies. It only affects the vast stretches of emptiness between them. The universe is expanding on the largest scales while remaining stable on the smaller ones. The interplay between gravity and expansion is what gives the cosmos its texture. Gravity acts as the great gatherer, pulling matter together to form stars, galaxies, and planets. The architecture of creation. Expansion, driven by dark energy, is the great disperser, pushing everything apart, diluting the density of matter, and spreading galaxies across the endless void. The result is a cosmic tug-of-war, with galaxies caught between the embrace of gravity and the outward thrust of the expanding universe. Over the next few trillion years, this expansion will continue to define cosmic destiny. If dark energy remains constant, galaxies outside our local group will accelerate away until their light can no longer reach us. The universe will enter an era known as the Cosmic Dark Age, when only nearby galaxies will remain visible. In that distant future, any intelligent beings still observing the sky may see a lonely, static cosmos, unaware that billions of galaxies once surrounded them. The grand story of the expanding universe will be hidden from view, buried in a past no telescope could ever retrieve. And yet, there is a strange beauty in this inevitability. Expansion is the universe's way of evolving, a reminder that change is written into the fabric of existence itself. Everything we know, everything that exists, is part of this motion. From the birth of galaxies in the early universe to the slow drift of entire clusters billions of years later. Even the atoms in our bodies are expanding apart, infinitesimally, as space itself stretches. We are participants in this grand unfolding, not observers standing outside it. The universe's expansion also holds the key to one of astronomy's greatest tools, the phenomenon that allows us to measure this cosmic stretching, to know how fast galaxies are moving away and how far back in time we are looking. This phenomenon, as it turns out, is encoded in the very light of the galaxies themselves. Light is the universe's storyteller. Every beam that travels through the cosmos carries with it a record, not just of where it came from, but how the universe has changed along the way. To astronomers, light is both map and time machine, a messenger from distant galaxies that encodes the secrets of cosmic motion. And at the heart of that message lies one of the most important and mysterious clues in all of astrophysics: the redshift. The concept of redshift is rooted in a simple, familiar principle: the Doppler effect. You've experienced it countless times on Earth. When an ambulance speeds toward you, its siren sounds high-pitched. When it passes and moves away, the pitch drops lower. That change occurs because the sound waves are compressed as the source moves toward you and stretched as it moves away. Light behaves in exactly the same way. When a star or galaxy moves toward us, its light waves are compressed, shifting toward the blue end of the spectrum, a blue shift. When it moves away, its light waves are stretched, shifting toward the red end, a redshift. But the redshift we observe in distant galaxies is far more profound than the simple Doppler effect of motion through space. It's not just that galaxies are moving away from us. Space itself is expanding, stretching the very wavelengths of light as they travel. Imagine painting red stripes on a rubber band and then stretching it. The stripes spread apart, lengthening the distance between them. Similarly, as the universe expands, the light waves from distant galaxies are stretched to longer wavelengths, making them appear redder. The farther that light has traveled, the more space has expanded, and the redder it becomes. Astronomers use this cosmic stretching to measure two essential things: how far away a galaxy is and how fast it's receding from us. The degree of redshift, how much the light has been stretched, tells us the galaxy's recession velocity, while its brightness or other known properties help estimate its distance. When Edwin Hubble first plotted these values for numerous galaxies in the 1920s, he found a striking linear relationship. The farther away a galaxy was, the greater its redshift, meaning the faster it was moving away. This became the foundation of Hubble's law, the discovery that revealed the universe itself is expanding. In technical terms, astronomers quantify redshift with a simple parameter, z, defined as the fractional change in wavelength. A galaxy with z equals 1 has its light stretched so that its wavelength has doubled. A galaxy with z equals 10 has its light stretched 11-fold. For nearby galaxies, z is small, fractions of 1. But for the most distant galaxies ever observed by the James Webb Space Telescope, z values can reach beyond 13, meaning the light has been stretched more than 14 times its original wavelength. Those galaxies emitted their light just a few 100 million years after the Big Bang, and it has taken more than 13 billion years to reach us. Redshift is not just a measurement of distance, it's a measure of time itself. Every redshifted photon carries with it the imprint of cosmic history. By studying how the light of galaxies changes with increasing redshift, astronomers can reconstruct the universe's timeline, how galaxies formed and evolved, how the rate of expansion changed, and how dark energy began to dominate. In essence, redshift is the heartbeat of the cosmos, the rhythm by which astronomers chart its growth and transformation. One of the most beautiful examples of this comes from the cosmic microwave background, the oldest light in the universe. When it was first released, about 380,000 years after the Big Bang, it was searingly hot radiation in the visible and infrared range. Over billions of years, as the universe expanded, that light was stretched, redshifted, by a factor of about 1,100, cooling into the faint microwave glow we detect today. What we see as the cosmic microwave background is, in fact, light stretched across 13.8 billion years of cosmic expansion. But redshift doesn't only tell us about distance, it also reveals the structure and motion within galaxies. Through a technique called spectroscopy, astronomers break starlight into its component colors, its spectrum, and analyze the fine lines created by elements like hydrogen, helium, and oxygen. When these lines shift toward the red, they reveal how fast the galaxy, or even specific regions within it, are moving away. This allows scientists to map rotation curves, study galactic dynamics, and measure how fast stars orbit their centers. Insights that led to the discovery of dark matter, since the visible mass alone couldn't explain the speeds observed. The farther we look, the more redshift dominates our view of the cosmos. Galaxies at extremely high redshifts, the ones seen by telescopes like Hubble Deep Field and James Webb, are so distant that their light is stretched beyond the visible spectrum into the infrared. That's why Webb was designed to see in infrared, to look deep into the redshifted past of the universe, where the first galaxies were forming out of darkness. Each faint smudge in those deep images represents light that began its journey billions of years before the Earth existed, stretched by the growth of space as it traveled. Redshift is, therefore, the language of the expanding universe, the way the cosmos tells us where and when we are looking. Every wavelength of light carries with it a story of motion, distance, and time. The reddest galaxies are not only the farthest, they are the oldest, frozen snapshots of what the universe looked like at its dawn. When astronomers observe them, they are effectively watching the universe in its infancy, witnessing the formation of the first stars, the first black holes, and the earliest stirrings of structure in a once dark cosmos. And yet, redshift also hints at a limit to our vision. The farther we look, the more the expansion stretches light until it fades beyond detectability. Beyond a certain point, the redshift becomes so extreme that the light can no longer reach us at all. Those galaxies lie beyond our observable horizon, forever hidden in the unobservable realm. What exists there, beyond the edge of light, is one of the greatest mysteries in cosmology. We've measured how space stretches, how galaxies move, and how time itself unfolds in the language of light. But there remains a boundary, a cosmic frontier, where observation ends and speculation begins. Beyond that horizon, beyond the reach of even the most powerful telescope, may lie an infinite continuation of the universe, or something stranger still. When we speak of the observable universe, we're not describing the entirety of existence, only the part we can see, the part from which light has had time to reach us since the dawn of creation. Beyond that glowing sphere of visibility, stretching some 93 billion light-years across, lies a realm we can never directly observe. Not because it isn't there, but because the light from it hasn't had time to arrive. This boundary is called the cosmic horizon, and it is not a physical wall, but a limit imposed by the very nature of space, time, and light. Beyond it, the universe continues, perhaps endlessly, into an infinity of galaxies, stars, and worlds that will forever remain hidden from our eyes. So what lies beyond the observable edge? That is one of the most haunting questions in all of science. The simplest answer, and the one most cosmologists accept, is that the universe doesn't suddenly end beyond what we can see. There is no cosmic cliff where galaxies stop existing. Instead, space likely continues in all directions, just as rich, just as full of matter and energy as the part we can observe. The galaxies beyond our horizon are not fundamentally different from those within it. They are simply too far away for their light ever to reach us. The expansion of the universe has carried them beyond the speed at which light can bridge the gap between us. They are not lost because they vanished, but because the fabric of space itself is stretching faster than light can traverse it. Imagine blowing up a balloon with tiny dots drawn on its surface. As the balloon inflates, each dot represents a galaxy. The farther apart the dots, the faster they recede from one another. From any given dot's perspective, there is a horizon beyond which no other dots can be seen, not because they cease to exist, but because the balloon's surface is expanding too quickly for any signal to travel across. That's our cosmic situation. From our vantage point within the Milky Way, the universe seems to fade into invisibility at the horizon. But beyond that boundary, galaxies continue endlessly, each with its own horizon, its own unseeable realm. The staggering implication is that the total universe may be billions, trillions, or even infinite times larger than the portion we can observe. The observable universe is merely a bubble, a single glowing patch within an ocean of cosmic reality. Every observer, no matter where they are, has their own observable sphere, bounded by their own horizon. If the universe is truly infinite, then there are infinitely many such spheres, each centered on a different observer, each filled with galaxies, stars, and possible life. Somewhere beyond our horizon, there may exist galaxies identical to ours, and perhaps, though unimaginably distant, even versions of ourselves, separated not by space in the ordinary sense, but by unbridgeable expanses of space-time. Some cosmologists suggest that the universe is flat and infinite, based on measurements of the cosmic microwave background radiation. If this is true, then what we see, the 2 trillion galaxies within our observable sphere, is just the tiniest fraction of an endless expanse. Even if space isn't infinite, it may be so vast that our observable patch is indistinguishable from a drop of water in a cosmic ocean. In such a universe, there could be quadrillions of galaxies, each with billions of stars, each surrounded by planets that will never know of our existence. Others take the idea even further, proposing that our universe may be just one bubble among many in a grander multiverse. According to some interpretations of cosmic inflation, the rapid expansion that occurred in the earliest fractions of a second after the Big Bang, space could be eternally inflating, spawning countless pocket universes like ours, each with its own laws of physics, its own forms of matter, its own possibilities. In this view, the cosmos we inhabit is only one of many universes, a single note in an infinite symphony of creation. Some may contain galaxies larger or smaller than ours. Others may have no stars at all, only black holes or exotic forms of energy. The concept stretches imagination to its breaking point, but it arises naturally from the mathematics of modern cosmology. Yet, even if the multiverse remains speculative, the existence of the unobservable universe beyond our cosmic horizon is almost certain. Its presence is written into the smoothness of the cosmic microwave background, the faint afterglow of the Big Bang. The uniform temperature of that radiation across the sky suggests that regions far beyond what we can see once interacted, meaning that space must extend much farther than our horizon allows. It's as if we're trapped inside a tiny bubble of visibility, while the true scale of existence stretches infinitely outward, silent and unreachable. What's most humbling about this truth is that we will never, no matter how advanced our technology becomes, see beyond that boundary. The universe is expanding too quickly. Even light, the fastest messenger in the cosmos, cannot outpace the swelling of space. As time goes on, the horizon will grow smaller, not larger, as more galaxies are carried beyond reach by dark energy's relentless push. The universe is showing us less and less of itself with each passing billion years, not because it's shrinking, but because it's accelerating into invisibility. So the next time you look at the night sky and feel overwhelmed by its vastness, remember this: everything you see, every star, nebula, and galaxy, is confined within a cosmic bubble, a finite window into an infinite expanse. Beyond it lies more of everything, more galaxies, more stars, more mysteries, and perhaps more life. Our observable universe, for all its immensity, is only the smallest fraction of the grand design, the tiniest glimmer in an ocean of eternity. And what's even more profound is that all of it, everything within and beyond our horizon, traces its origins back to a single moment, a singular act of creation when time and space themselves were born. To understand what might lie beyond the edge, we must look back to the very beginning, to the birth of everything, in a universe that emerged from nothing. Every galaxy, every star, every planet, every atom that makes up you and me, all of it, every piece of matter and energy in the universe, once existed in a single, infinitesimal point. About 13.8 billion years ago, the entire cosmos was compressed into a state of almost unimaginable density and heat. There was no space as we know it, no time, no up or down, no galaxies or stars, only an immense potential, a kind of cosmic seed containing everything that would one day become the universe. Then, in a moment that defies all comprehension, that point expanded. Not into empty space, but into itself. Space itself began to grow, and in that instant, the universe was born. We call this beginning the Big Bang, though the term can be misleading. It wasn't an explosion in the traditional sense. There was no detonation in some pre-existing void. Instead, it was the expansion of space from within itself, the moment when time and space began. Before the Big Bang, the concept of before becomes meaningless because time itself did not yet exist. The Big Bang was not an event in the universe. It was the event that created the universe. In its first fraction of a second, the universe underwent a phase of unimaginable transformation known as cosmic inflation. In an instant, the fabric of space expanded exponentially, growing from subatomic scales to macroscopic size in less than a trillionth of a second. This inflationary burst smoothed out the universe, stretching quantum fluctuations into the tiny variations in density that would later seed galaxies and clusters. Those minute differences, ripples in the newborn universe, are written into the cosmic microwave background radiation, the faint afterglow we can still detect today, a baby picture of the cosmos when it was just 380,000 years old. After inflation ended, the universe was still a seething ocean of energy, too hot for atoms to exist. It was filled with a dense plasma of particles, protons, neutrons, electrons, and photons, colliding in a chaotic dance. As it expanded, it cooled. Within minutes, protons and neutrons began to fuse, forming the first atomic nuclei, hydrogen, helium, and traces of lithium, in a process called Big Bang nucleosynthesis. These simple elements became the building blocks of everything that would follow. For hundreds of thousands of years, the universe remained an opaque fog of charged particles and radiation. But as it continued to cool, the electrons finally slowed enough to bind with nuclei, forming neutral atoms. The universe became transparent, allowing light to travel freely for the first time. That ancient light still travels today, filling all of space as the cosmic microwave background, a ghostly echo from the universe's earliest dawn. From that moment onward, the universe entered a long era of darkness, the cosmic dark ages. There were no stars, no galaxies, only vast clouds of hydrogen and helium drifting through expanding space. Gravity, patient and inexorable, began to do its work, pulling matter together into denser regions. Slowly, over hundreds of millions of years, these clumps grew, compressing under their own gravity until the first stars ignited. Those first stars, massive, short-lived titans, illuminated the universe for the first time. Their ultraviolet light tore apart the hydrogen fog, ending the dark ages in an event known as rionization. When those stars died in violent supernovae, they scattered heavier elements, carbon, oxygen, iron, into the cosmos, enriching the gas clouds that would form the next generations of stars and planets. From their ashes, the first galaxies began to take shape, small and irregular at first, later merging to form the grand spirals and ellipticals we see today. All of this, the galaxies, the stars, the planets, came from that first explosion of expansion. Every atom in your body was once part of that primordial fireball. The calcium in your bones, the iron in your blood, the carbon that forms your cells. All of it was born from processes that began in the Big Bang and continued in the hearts of long-dead stars. We are not separate from the universe's beginning. We are its direct descendants. We are, quite literally, the universe made conscious, looking back upon itself and wondering how it all began. The beauty of the Big Bang theory is not just that it explains how the universe started, but that it predicts what we should still see today. And every prediction has been confirmed. The cosmic microwave background exists exactly as the theory describes. The abundance of light elements matches the calculations. The galaxies we see are receding just as the expansion demands. And the oldest stars show ages that trace back to roughly the same moment, 13.8 billion years ago, give or take a few tens of millions. And yet, for all our understanding, the Big Bang still leaves us with haunting questions. What caused it? Why did the universe begin at all? Did it emerge from nothing, or from something that came before? Perhaps another universe, another cycle of cosmic birth and death. Some theories suggest that our universe may be just one in a vast multiverse, each universe a bubble expanding in its own dimension. Others propose that the Big Bang may have been the bounce of a previous universe collapsing in on itself, a cosmic heartbeat of endless creation and renewal. Whatever the true answer, the Big Bang marks the ultimate origin of time, matter, and energy. From that singular point of infinite density emerged the framework of everything we know, from the laws of physics to the seeds of galaxies. And even now, billions of years later, the universe still carries the imprint of that beginning. Every star that shines, every galaxy that spins, every breath we take, all of it is an echo of that first explosion of light. To stand under the night sky is to stand in the aftermath of the Big Bang, to gaze across space and time and see the continuing story of that original moment. And at the centers of many galaxies, including our own, lies a mysterious force born from the same cosmic processes. Engines so powerful that they can reshape entire galaxies. These are the black holes, the dark hearts of the universe, and they hold the next key to understanding how everything we see came to be. At the center of nearly every large galaxy, hidden behind swirling clouds of dust and blazing starlight, lies an object so extreme that it bends the very fabric of reality, a supermassive black hole. These titans are among the most powerful and enigmatic entities in the cosmos, with masses ranging from millions to billions of times that of our Sun. They are not merely destructive voids, as popular imagination often suggests. They are cosmic engines, shaping galaxies, governing their growth, and perhaps even playing a key role in the evolution of the universe itself. In our own Milky Way, this central giant is called Sagittarius A. It sits about 26,000 light-years from Earth, buried deep in the galactic core, where stars orbit at astonishing speeds. Sagittarius A has a mass of roughly 4 million suns, compressed into a space smaller than our solar system. Around it, stars whip through space at thousands of kilometers per second, while near its event horizon, the point of no return, time itself slows to a crawl. For centuries, its presence was only suspected, inferred from the strange orbits of nearby stars. But in 2022, the Event Horizon Telescope, EHT, a planet-sized network of radio observatories, captured the first direct image of Sagittarius A, a glowing ring of light surrounding a dark shadow, the signature of space-time twisted by gravity to its breaking point. Black holes, like Sagittarius A, are not rare anomalies. Observations have shown that almost every galaxy has one at its core, and the size of that black hole is closely linked to the size and mass of its host galaxy. This intimate connection suggests that galaxies and their central black holes evolved together, each influencing the other over billions of years. But how can something that swallows all light possibly create and shape galaxies? The answer lies in the tremendous energy that surrounds a black hole, not within it. When gas, dust, and even stars fall toward a black hole, they don't plunge straight in. Instead, they spiral around, forming an accretion disk, a swirling maelstrom of superheated matter rotating at near-light speeds. Friction and magnetic forces within this disk generate intense heat and radiation, releasing more energy than the combined output of every star in the galaxy. These luminous central regions are known as active galactic nuclei, AGN, and when they shine brightly enough, we call them quasars, the most powerful beacons in the universe. Quasars can outshine their entire host galaxies, pouring out energy equivalent to trillions of suns. They are often seen in the early universe, where galaxies were young and gas was plentiful. As the black hole feeds, it drives fierce jets of charged particles that shoot out from its poles, extending for hundreds of thousands of light years into intergalactic space. These jets can heat and stir surrounding gas, triggering or suppressing star formation depending on how they interact with their environment. In this way, black holes act as both creators and regulators, controlling the pace of galactic evolution. Astronomers have discovered that galaxies hosting actively feeding black holes often experience bursts of star formation, followed by periods of dormancy. When a black hole's jets and winds blast through its host galaxy, they can blow away the gas that would otherwise form new stars, effectively quenching the galaxy's growth. On the other hand, those same outflows can also compress nearby clouds of gas, sparking the birth of new stars. The relationship is delicate, almost symbiotic, a feedback loop between cosmic destruction and creation. What's even more remarkable is how precisely a galaxy's overall structure seems to correlate with its black hole. The more massive the black hole, the more massive the surrounding galactic bulge. This suggests that as galaxies grow, by consuming gas, merging with others, or forming new stars, their central black holes grow too, feeding on the same inflowing material. During galactic collisions, for example, two supermassive black holes can spiral together, eventually merging into an even larger one, releasing gravitational waves that ripple across the universe. These cataclysmic events not only reshape galaxies, but also radiate energy that can be detected billions of light years away. Faint tremors in space-time that tell us of cosmic unions long past. And yet, for all their power, black holes are not mere destroyers. They are cosmic recyclers, engines that convert matter into energy and redistribute it throughout the galaxy. Without them, galaxies might grow too large, form too many stars, or burn through their gas too quickly. Black holes, in their paradoxical nature, bring balance, regulating how galaxies evolve and how long they remain active. Even the space around them is a realm of wonder. Near a black hole's event horizon, the pull of gravity is so immense that it warps light, bending it into surreal arcs and rings. Time slows dramatically, stretched by gravity's relentless hand. If you could orbit just outside the event horizon, you would see the entire universe's future unfold in fast-forward, while mere moments passed for you. It's not just science fiction, it's the strange, beautiful reality of Einstein's general relativity made visible. On cosmic scales, supermassive black holes may also have played a role in shaping the large-scale structure of the universe itself. In the early epochs, their powerful quasars lit up the darkness, flooding intergalactic space with radiation that helped ryanize the universe. The jets they expelled may have seeded the cosmic web with magnetic fields and energy that influenced how galaxies formed along filaments of dark matter. In this sense, black holes were not merely passengers in cosmic evolution. They were architects, helping to sculpt the grand patterns of matter and energy that defines the universe today. And yet, their paradox endures. At their core lies a mystery that defies our understanding. According to general relativity, a black hole's center contains a singularity, a point of infinite density where the known laws of physics break down. Time and space, as we understand them, cease to have meaning. What truly happens at that point remains unknown. Some physicists believe that the singularity may be a gateway to new physics, or perhaps even to other universes, a connection between the visible cosmos and a deeper, hidden reality. But whether or not they hold portals to other worlds, black holes remain the heartbeats of galaxies, the silent conductors of the cosmic symphony. They embody the universe's duality, creation and destruction, chaos and order, life and death, all interwoven in the same gravitational rhythm. And as galaxies collide and merge under their influence, something extraordinary happens. Beauty emerges from chaos. The universe paints its grandest masterpieces, not in stillness, but in motion, through the violent ballet of colliding galaxies and reborn stars. In the vast darkness of the cosmos, creation often wears the face of destruction. Galaxies, those sprawling cities of stars, are not static islands drifting in peace. They are restless, dynamic, and destined to collide. And when they do, the universe creates some of its most spectacular and beautiful phenomena. It's a paradox both violent and elegant. Out of chaos comes order. From cosmic collisions come new worlds, new stars, and new galaxies. Galactic collisions are inevitable in a universe ruled by gravity. Every galaxy, including our own Milky Way, is in motion, pulled and influenced by the invisible threads of dark matter that weave the cosmic web together. Over billions of years, these gravitational interactions bring galaxies together like celestial dancers drawn into one another's arms. They do not smash in a single explosive moment as solid objects might. Instead, they intertwine slowly, their stars, gas and dust stretching and merging over hundreds of millions of years. From our limited human perspective, it's easy to imagine such encounters as violent cataclysms, galaxies shattering, stars colliding, worlds destroyed. But in truth, the vast distances between stars mean that very few actually collide directly. Instead, the immense gravitational tides from each galaxy tug on the other, warping their shapes, flinging streams of stars and gas into space, and igniting brilliant waves of star formation. It is an intricate and beautiful dance, one that transforms both partners forever. When two galaxies begin to merge, their graceful spirals are distorted into surreal new forms. Long, luminous filaments known as tidal tails arc out into the void, stretching for hundreds of thousands of light years. These tails glimmer with newborn stars, the result of collapsing gas clouds compressed by the encounter. Some galaxies form rings when one passes directly through the center of another, sending circular waves rippling outward like the rings formed when a stone is thrown into water. Others twist into strange butterfly-like shapes, as gravity tears and reshapes their delicate structures. One of the most breathtaking examples of this cosmic artistry is the antennae Galaxies, located about 45 million light-years from Earth. These two colliding spirals are locked in a slow embrace, their elongated tidal tails stretching into space like the antenna of an insect. In their overlapping cores, gas clouds are colliding, triggering a starburst, an eruption of star formation, producing thousands of new suns every year. The collision has turned chaos into creation, lighting up the darkness with the birth of countless stars. Starbursts like this are among the most fertile moments in a galaxy's life. When two galaxies merge, their gas is funneled inward toward the center, where it compresses under gravity's pressure. This triggers rapid, large-scale star formation, a kind of cosmic wildfire that consumes available gas in a fraction of the time it would normally take. Entire clusters of massive, hot blue stars are born, burning brightly and dying young in supernova explosions that seed their surroundings with heavy elements, the building blocks of planets and life. In the aftermath of these mergers, the galaxies are forever changed. Some may eventually settle into new elliptical forms, their spiral arms erased by gravitational chaos. Others may retain fragments of their original structure, becoming hybrid galaxies with both disk and bulge components. Over time, the intense starbursts subside, leaving behind a calmer but older galaxy, one enriched by the ashes of countless dead stars. Even the central supermassive black holes of each merging galaxy are destined to meet, spiraling toward one another and eventually merging in a cataclysmic burst of gravitational waves, sending ripples through space-time itself. Our own Milky Way is on this same path. Roughly 4 billion years from now, we will collide with our nearest large neighbor, the Andromeda Galaxy. The two spirals are currently rushing toward each other at about 110 kilometers per second, and when they meet, their shapes will warp and twist into one another. Over the course of 1 billion years, they will merge completely, forming a massive elliptical galaxy that astronomers have already named Milky Way. Though this sounds apocalyptic, the view from Earth, or whatever worlds may exist then, will be breathtaking. The night sky will be ablaze with streams of stars from Andromeda, its core stretching across the heavens. In that distant epoch, the descendants of humanity may witness the most magnificent sight in cosmic history, two galaxies becoming one. It is through such mergers that galaxies grow. Through destruction comes rebirth. In the early universe, collisions were far more common, as galaxies were packed more closely together in the dense cosmic web. The great spirals we see today, like the Milky Way and Andromeda, were forged from countless mergers of smaller proto-galaxies. Each collision added mass, stirred gas, and kindled new generations of stars. The very atoms in your body, the oxygen you breathe, the carbon that forms your cells, were likely born in such cosmic events, forged in the furnaces of stars ignited by ancient galactic collisions. Even the most serene galaxies we see in the sky carry the scars of this turbulent past. The faint streams of stars and gas that surround many galaxies, visible only in deep exposures, are the ghostly remnants of long-forgotten mergers. They are the fossils of cosmic evolution, evidence that chaos and creation are inseparable. The beauty of these collisions lies not only in their visual majesty, but in what they symbolize. That creation is not a process of peace, but of transformation. The universe is not static, it is alive, evolving through conflict, gravity, and time. Every galaxy, every star, every atom has been shaped by this restless cycle of destruction and renewal. When you look up at the stars, remember that their light, calm, constant, and serene, is born from a history of violence on a cosmic scale. Galaxies have collided, merged, and reborn to create the structures that now fill the universe with light. From chaos, beauty arises. From death, life emerges. This is the universe's most profound truth. Creation and destruction are two sides of the same cosmic coin. And amidst this endless cycle, somewhere within one spiral arm of a quiet galaxy, a small planet formed around a yellow star, a place where consciousness arose to look back upon the cosmos and marvel at the very chaos that made it possible. In the boundless immensity of the cosmos, our entire existence, everything we have ever known, built or dreamed, is contained within a single, fragile speck of dust, adrift in an ocean of galaxies. Our solar system, orbiting an ordinary star halfway along one arm of the Milky Way, is less than a microscopic dot in a single galaxy among 2 trillion others. When viewed from this cosmic scale, all of human history, every empire, every discovery, every heartbeat, becomes almost imperceptible, a brief flicker in an endless sea of time and space. And yet, that realization is not a diminishment of our significance. It is the very source of our wonder. Our home lies on the edge of the Milky Way's Orion Arm, a minor spiral branch tucked between 2 larger ones, the Sagittarius and Perseus arms. Here, in a quiet suburb of our galaxy, our Sun orbits the galactic center once every 230 million years. It has made that journey around the Milky Way's heart only about 20 times since it formed. The Milky Way itself, vast beyond comprehension, stretches more than 100,000 light-years across and contains roughly 400 billion stars. And our Sun is just one of them. If our entire solar system were shrunk to the size of a grain of sand, the Milky Way would still be a structure thousands of kilometers wide. And yet, this galaxy, magnificent as it is itself only one among the countless others that populate the universe. When we lift our eyes to the night sky, we are looking outward from within this grand spiral disk, seeing only a tiny fragment of what surrounds us. The faint river of light that arcs across the sky, the Milky Way band, is not a separate structure, but the dense, glowing plane of our own galaxy seen from the inside. Every glimmer in that ribbon is a sun, many with their own worlds, their own possibilities. The light from those distant stars has traveled for tens of thousands of years to reach us, crossing the vast gulf of interstellar space. Some of those stars may no longer even exist, their light still journeying across the darkness long after their fires have gone out. And yet, beyond those stars lie other galaxies, each one a universe unto itself, containing billions of suns and perhaps trillions of planets. To grasp the scale, imagine the Milky Way as a single grain of sand. The nearest large galaxy, Andromeda, would be another grain about 2 meters away. The entire local group, our galactic neighborhood, would fit into the volume of a small room. But the observable universe, filled with 2 trillion galaxies, would be a beach stretching across entire continents, an infinite expanse of shining grains, each one a galaxy, each one containing the potential for life, for beauty, for meaning. Our solar system, nestled within this immensity, is a remarkably small and delicate oasis. The Sun, a middle-aged star about 4.6 billion years old, is neither exceptional nor rare. Around it orbit 8 planets, dozens of moons, and countless asteroids and comets. Earth, our home, is one planet among billions. Yet it is here, on this tiny world, that the universe has become aware of itself. It is here that matter, once born in the heart of ancient stars, has learned to question its origins. Every atom in our bodies was forged in the furnace of a long-dead sun. We are the children of stardust, the descendants of galaxies that collided, stars that died, and elements that formed in supernova fire. The same cosmic processes that shaped the Milky Way also shaped us. We are not apart from the universe. We are a way for the universe to know itself. From our human perspective, the distances involved are staggering beyond words. The nearest star system, Alpha Centauri, is about 4.3 light-years away. That's roughly 40 trillion kilometers. The light that leaves that star tonight won't reach us until 4 years from now. The nearest galaxy beyond our own, Andromeda, lies 2.5 million light-years away. The light we see from it tonight began its journey when early humans first began to use simple tools. The farthest galaxies we can detect, revealed by telescopes like James Webb, are so distant that their light has been traveling for over 13 billion years, showing us the universe as it was when it was still in its infancy. Standing on Earth, beneath the thin blue film of our atmosphere, we inhabit a world that seems enormous to us, a world of oceans, mountains, and continents. Yet from space, Earth is little more than a pale blue dot, as the late Carl Sagan so famously described it, a mote of dust suspended in a sunbeam. Every war, every triumph, every love story, every act of creation or destruction, all of it unfolds on that tiny pixel of light. When the Voyager 1 spacecraft turned back in 1990 to capture that now legendary image of Earth from 6 billion kilometers away, it gave us a perspective both humbling and profound. We are small, yes, but our smallness is what makes our existence so precious. It is easy, when faced with such immensity, to feel insignificant. How can one human life matter in a universe of trillions of galaxies? But significance is not measured by size or scale. It is measured by awareness. The fact that the universe, through us, can look back and contemplate its own origins is perhaps the most extraordinary fact of all. Out of all the stars and galaxies, we are one of the few, perhaps the only, forms of matter that can question itself, that can feel wonder, that can love. We are, in a very real sense, the cosmos made conscious. The same laws that govern the motion of galaxies govern the beating of our hearts. The atoms in our blood trace their ancestry to supernovae. The gravity that binds stars into galaxies also binds us to our planet and to one another. The scale may be unfathomable, but the connection is intimate. We are not lost in the vastness. We belong to it. And yet, even as we marvel at our place in this grand tapestry, the universe continues to expand, carrying distant galaxies away faster and faster. The cosmic horizon recedes, and much of what exists today will one day vanish from our view. It reminds us that our time, both as individuals and as a species, is fleeting, a brief moment in a story that began long before us and will continue long after. But perhaps that is what makes it beautiful, that we, in this moment, in this tiny corner of one spiral arm of one galaxy among trillions, have the privilege of witnessing it. We are here, for a short while, to look out into the infinite, to wonder, to ask, to dream. And as we watch galaxies drift away into the distance, carried by the ever-stretching fabric of space, we begin to understand the profound truth that not all of the universe will remain visible to us forever. Beyond our reach, beyond even the speed of light, the cosmos continues its expansion, revealing the limits not only of what we can see, but of what we can ever know. The universe is vast beyond comprehension, but even that vastness comes with boundaries. Not walls, not edges, but limits written into the very fabric of space-time. We live inside what astronomers call the cosmic horizon, the farthest distance from which light has had time to reach us since the birth of the universe, 13.8 billion years ago. It defines the visible boundary of our reality. the sphere of the observable universe, roughly 93 billion light-years across. Everything beyond it exists, but its light has not yet arrived, and in many cases, it never will. For even as we look outward, the universe itself is racing ahead of us, expanding faster than light can travel. This concept is one of the most mind-bending truths in all of cosmology. It challenges our most basic intuitions about space, time, and motion. To understand it, we must first let go of the idea of galaxies speeding through space, like ships moving through water. The universe's expansion is not the movement of galaxies through space. It is the stretching of space itself. The galaxies are not racing away. The fabric of space-time between them is expanding. And because there's no limit to how much space can expand, there's no limit to how fast distant galaxies can appear to recede. This expansion was first discovered by Edwin Hubble, who found that distant galaxies show a consistent redshift. Their light stretched toward longer wavelengths as they move away. Later discoveries revealed something even more surprising. The expansion isn't slowing down as once thought, but accelerating, driven by the mysterious force we call dark energy. This acceleration has profound consequences for the future of observation. The farther a galaxy is from us, the faster it appears to recede. At a certain distance, about 14 billion light-years away, galaxies are receding from us at the speed of light due to the expansion of space. Beyond that point, they move away even faster. Not because they break the laws of physics, but because those laws apply locally. They govern the motion of objects through space, not the expansion of space itself. And as a result, light emitted by galaxies beyond this critical threshold will never reach us, no matter how long we wait. The universe is quite literally outrunning its own light. This means that we will never see the entire universe. No telescope, no matter how powerful or advanced, can pierce the cosmic horizon. Beyond it lies a realm forever hidden, an unobservable universe that could be infinitely larger than what we can detect. The galaxies beyond that boundary are like ships sailing away on a tide that grows faster with every passing moment. Their light, stretched and dimmed by expansion, fades until it disappears completely, redshifted into wavelengths so long that even our most sensitive instruments can no longer detect them. And the truly haunting part is that this process is ongoing. Every day, every second, more galaxies slip beyond the horizon. Not because they cease to exist, but because the space between us and them expands faster than their light can close the gap. The universe is becoming increasingly isolated as cosmic expansion drives distant regions forever out of communication. Billions of years from now, even the nearest galaxies outside our local group will have drifted so far away that their light will no longer reach us. In the far future, an observer in our galaxy will look into the night sky and see only the faint glow of their own galactic neighbors. The rest of the universe, all the billions of galaxies that once filled the sky, will be gone from view. The cosmic horizon will have shrunk to encompass only our small cluster of galaxies, adrift in an expanding void. Those future astronomers, if they exist, may look out and believe their universe is small, static, and lonely, unaware that beyond their invisible boundary lies a vast cosmos that once shimmered with light. This fate is not mere speculation. It's the logical consequence of our current understanding of cosmology. The universe is expanding at an accelerating rate, driven by dark energy, which accounts for about 68% of its total content. If this acceleration continues indefinitely, the cosmic horizon will continue to shrink in relative terms, erasing more of the universe from visibility as time goes on. The galaxies that are already distant will be the first to vanish from our cosmic view, their light redshifted until it merges with the background darkness. Eventually, Only the faint afterglow of the cosmic microwave background, the oldest light in existence, will remain, stretched beyond recognition into radio waves, until even that fades away into silence. This is the ultimate isolation, a universe that once was vibrant and interconnected, gradually fragmenting into countless separate islands, each surrounded by a sea of nothingness. It's a vision both beautiful and melancholy. In the far future, when the stars have burned out and galaxies drift apart beyond sight, the universe will enter its twilight, a cosmic night that will never end. And yet, this knowledge does not make our current moment less meaningful. It makes it more precious. We exist at a rare time in cosmic history, when the universe is still young enough and expansion slow enough that we can see across billions of light years. We can observe the ancient galaxies, the echo of the Big Bang, and the grand web of structure connecting it all. We are witnessing the cosmos in its most glorious phase, the age of light. Every image captured by telescopes like Hubble and James Webb is a time capsule from this fleeting era. The deep field images that reveal thousands of galaxies in a patch of sky, smaller than a grain of sand. They are windows into the vanishing universe. What we see now will one day be invisible, erased by the accelerating tide of dark energy. The cosmic horizon reminds us that even the infinite has limits, that knowledge itself is bounded by the speed of light and the expansion of space. But perhaps there is beauty in that mystery. The fact that we cannot see it all gives the universe a kind of poetic incompleteness, a reminder that wonder is endless, that discovery is eternal. Beyond the horizon, beyond the reach of light, the cosmos continues in silence. There are galaxies being born there, stars igniting, worlds spinning under alien suns, all forever unseen, yet still part of the same creation that made us. And so we are left to ponder not just what lies beyond, but why it exists at all. Why there is something rather than nothing. Why the universe is so vast. And why, within all that infinite darkness, a tiny planet around an ordinary star has become self-aware enough to ask the question. Why is the universe so vast? Why must it stretch across trillions of galaxies and billions of light years, filled with more stars than there are grains of sand on every beach on Earth? Why must existence be so overwhelming, so incomprehensibly huge, that our entire planet, our species, our every thought, is reduced to a microscopic whisper in the void? These are not questions science can fully answer. They belong to that hazy borderland between cosmology and philosophy, where numbers give way to meaning and facts give way to awe. We can measure the age of the universe, chart its expansion, and trace its history all the way back to the first fraction of a second after the Big Bang. We can model the birth of stars and the dance of galaxies. But when we ask why the universe exists at all, and why it is the way it is, so vast, so finely tuned for life, and so breathtakingly beautiful, we find ourselves staring into the greatest mystery of all. Perhaps the vastness is necessary. Perhaps the universe must be this immense, this ancient for life and for consciousness to arise. Stars must live and die to forge the elements needed for biology. Galaxies must collide to stir those elements into new generations of stars. Time itself must unfold over billions of years before planets form, oceans ripple, and minds emerge to contemplate their own origins. If the universe was smaller, younger, or shorter-lived, perhaps there would not have been enough time for starlight to sculpt matter into thought. It is possible, then, that the enormity of the universe is not an accident, but a requirement, a cosmic incubator vast enough to give birth to meaning. The philosopher John Archibald Wheeler once said, "We are participants in bringing into being not only the near and here, but the far away and long ago." Consciousness, in his view, is not an afterthought of creation, but a fundamental part of it, the universe knowing itself through us. In this sense, the universe is not vast despite us. It is vast because of us. It had to be this way for consciousness to awaken. Even on one small, fragile world orbiting an ordinary star in an unremarkable galaxy. Yet, there is another possibility, one even more humbling. Perhaps the universe is not vast for any reason at all. Perhaps it simply is, infinite, indifferent, and beautiful in its own right. The laws of physics do not require purpose. Galaxies do not spin for our sake, nor do stars burn to illuminate our nights. The universe existed long before us, and will continue long after we are gone. Our existence may be an accident, a fleeting anomaly in an indifferent cosmos. But even if that's true, isn't there something miraculous in the fact that we can see it, understand it, and feel wonder at all? We are tiny, yes, infinitesimally small in the scale of things, but we are also rare. Out of all the matter in the cosmos, we are part of the fraction that can ask, why? Hydrogen, helium, and carbon have combined in such a way that they can ponder their own existence. The same atoms that once burned in ancient stars now assemble into thoughts, memories, and questions. We are, as Carl Sagan said, a way for the cosmos to know itself. That is not insignificance, that is transcendence. Still, the question lingers like an echo in the silence of the stars. Why must the universe be so large for so little of it to be aware? If consciousness arose only here, in this tiny corner of one galaxy among trillions, does that not seem like a kind of cosmic loneliness? Or does it suggest that consciousness is inevitable, that somewhere, out there, in the unseeable reaches beyond our horizon, other minds are asking the same question, gazing at their own skies, wondering if they too are alone? Perhaps the universe's vastness ensures that consciousness does not exist only once. Perhaps its immensity is a safeguard against isolation, a cosmic guarantee that awareness will bloom in more than one place, in more than one form. Maybe the universe is so large because life itself is meant to be abundant, scattered across the galaxies like sparks in the dark. And if not, if we are truly alone, then our responsibility becomes even greater. For if consciousness has emerged only here on this small blue planet, then we are the universe's single voice. We are the only eyes through which it sees itself, the only minds through which it can reflect on its beauty. To waste that awareness, to fail to cherish this fragile world, would be to silence the only consciousness the cosmos may ever have. There's another possibility, one that blends science with mystery. Perhaps the universe is so vast because it must contain all potential outcomes, all possible worlds. Every galaxy, every star, every atom is one thread in an infinite tapestry of probability. The universe may not simply exist, it may explore every way it can exist. Out of that boundless diversity, consciousness was bound to appear somewhere. And here we are. No matter which interpretation you choose, whether cosmic necessity or chance, the result is the same. Awe. The kind of awe that silences words, humbles pride, and fills us with gratitude simply for being part of this story. We may never know why the universe is so vast, or why we are here to witness it. But the mystery itself may be the answer. For in seeking to understand, we give the universe something it would otherwise lack: meaning. And that meaning leads us to the final truth, that in a cosmos of trillions of galaxies and endless expansion, the most profound act we can perform is not to conquer the universe, but to wonder at it, to stand in awe beneath the stars and recognize that we are both infinitesimal and infinite, both transient and eternal. In the end, all our equations, telescopes, and theories bring us to a single, humbling truth. We are part of something far beyond our understanding. The universe, with its trillions of galaxies, its uncountable stars, its web of dark matter and invisible energy, is not merely vast, it is transcendent. It stretches not only across space, but across imagination itself. Every spark of light in the night sky, every shimmer of starlight that touches our world, is a reminder that we are participants in a grand and ongoing creation, a story still being written across the fabric of space-time. When we gaze up at the stars, we are looking into our own origins. The atoms that compose our bodies were forged in the hearts of long-dead stars. The iron in our blood, the calcium in our bones, the carbon in our cells. All of it was born from the fire of ancient suns that exploded billions of years ago. Those stars lived, burned, and died so that we could exist. We are not strangers in this cosmos. We are its continuation, its expression made conscious. To look at the universe, then, is to look into a mirror that reflects both infinity and intimacy. Every breath we take, every thought we think, is powered by processes that began long before Earth formed. The light from our sun carries the same physics that governs distant galaxies. The gravity that holds us to this planet is the same force that binds galaxies together and bends the paths of light through the cosmos. We are stitched from the same fabric as the stars, made of the same dust, following the same laws, bound to the same destiny. And yet, despite our smallness, our short lives, our fragility, we can understand. We can comprehend the age of the universe, measure the speed of its expansion, and detect the whisper of light from its birth. Through our instruments and our minds, we have extended our reach across billions of light years, touching the edge of the observable universe and peering back almost to the beginning of time itself. We have seen galaxies as they were when the cosmos was young, watched the birth and death of stars, and listened to the echoes of the Big Bang. The universe has given us eyes to see it, and curiosity to question it, and that, perhaps, is its greatest miracle. But for all that we've learned, the deeper truth is that the universe remains profoundly mysterious. The vast majority of it, 95%, is invisible, composed of dark matter and dark energy that we do not yet understand. Even time and space, those cornerstones of reality, may be illusions of deeper laws not yet known. The more we uncover, the more we realize how much remains hidden. Each discovery opens 1,000 new questions, and that endless curiosity is the heartbeat of our species, our role in this cosmic story. It is easy, when confronted with such immensity, to feel insignificant, to feel that we are too small to matter. But that perspective misses the truth. The universe is vast, yes, but its vastness does not diminish us. It includes us. Every human being, every planet, every star is a thread in its endless tapestry. We are not an accident within it. We are an expression of it. Our consciousness, our art, our love, our questions, these are not intrusions into the cosmos. They are the cosmos awakening to itself. And perhaps that is the deepest wonder of all. In a universe filled with silence, we are its voice. We are the means through which the universe observes, feels, and dreams. Every time we look up at the night sky, we fulfill that role, bridging the infinite with the intimate. The photons that left distant galaxies billions of years ago complete their journey when they meet our eyes. In that instant, the universe and the observer become one. So let us stand beneath the stars and feel both humbled and exalted. Humbled because we are small, fleeting, and fragile. Exalted because we are capable of perceiving the infinite, capable of love, curiosity, and awe. Every galaxy that spins in the distance, Every supernova that blooms and fades, every world that orbits a faraway sun, all of it is connected through the same cosmic lineage that produced us. We are, each of us, threads of the same ancient light. In a universe of trillions of galaxies, our lives might seem momentary, a flicker on a grain of dust orbiting an average star. But that flicker is not meaningless. It is precious beyond measure, because it carries the light of awareness. We are the witnesses of creation, the children of stardust who can look up and feel wonder. And perhaps that is the purpose of it all, not to understand every mystery, not to conquer the cosmos, but simply to stand in awe of it. To look out into the night, see those scattered diamonds of light, and realize that we belong to them, that we always have and always will. The universe may be infinite, but so too is our capacity for wonder. That, more than anything else, is what connects us to the stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.